I don't know, there was issue with Rahul Agarwal. Uh, any of your friend made contact with him, because while I was starting the recording mode on, possibly the Google Meet was referring that the Rahul Agarwal cannot be made presented. I think possibly in his account this kind of setting was there. So that's why the recording portion we will be sharing with him. But personally, if anyone want to contact with him that why this kind of difficulties he is finding, or if he have kind of alternative number, he can also join with. So I hope almost around 50 students have already joined, so we can start our today's session. Can we start? What do you prefer?
Yes, sir.
Okay. So let the others join in this sequence, but let us start our discussion from here. So today, it's very unfortunate that we can't take all of you to our illumination laboratory. Repeatedly during your utilization illumination classes, I have told you this is the biggest asset we have of electrical engineering department. And in India and also in Asia, possibly we are the only educational institute or university those who have a full-fledged illumination laboratory where we do measure several parameters starting from the photometry to the radiometry and also electrical phase measurements, human-centric phase measurements. So all the broad domains of illumination engineering are basically measured, tested, developed in our illumination lab. So that's why this is a biggest asset. Very unfortunate that because of this pandemic, we can't take all of you to our laboratory. And I am a bit hopeful that very soon this pandemic will be over and I can take all of you to our laboratory to feel the situations. Because possibly in your first semester also you haven't got the chance to come to our this darkroom laboratory. So if already you have gone through the today's experiment, I have made a small PowerPoint presentation base. So the experiment title is a calibration of a lux meter and measurement of horizontal intensity distribution from a lamp with a calibrated lux meter. So this is the title of the experiment. The idea is very simple. In our utilization classes, we were talking about the lamp, different light sources. We already have started. Once we are going to talk about the lamp, what are the fundamental parameters of a lamp is required to get it standardized to make it a proper specification. So one of the important parameter is luminous flux. That means light energy radiated per unit time, energy per time, dq dt. So that is a luminous flux, luminous energy once we are talking about. The issue is that once we are talking about the luminous flux, we never mention the direction. So that's why we need a specific parameter which helps us to measure the direction. So luminous intensity is that. Luminous intensity is the parameter which will give you the direction. So how can we define luminous intensity then? The luminous intensity will be defined like solid angular flux in a given direction. It's a solid angular flux in a given direction. So our concern is to measure the horizontal luminous intensity distribution from a light source, but using a calibrated lux meter. So what is lux meter? The lux meter is a device which is used to measure illuminance. So you might be a bit confused that what is the difference between illuminance, luminance. I already have told you in our utilization classes. This particular week, once we start that, we will talk about the different terminologies. Those sound similar, but there is a very interesting difference between them. Illuminance means luminous flux reaching on your receiver. So I am right now working from my home. Yesterday was in my chamber at university department. So in my tabletop, how much light is falling at each point, that will be designated by illuminance. What fraction of light is coming towards my eye, or what fraction of light is coming towards, say, directly from the light source or reflected from the source towards my eye, that will indicate the luminous intensity. So from the light source, how much is falling over a surface? That is illuminance at each point. If we can take a differential area of dA or maybe a big area of A, so phi by A, phi is the luminous flux coming out from a source divided by the area, that will give the idea of illuminance, or with the unit of illuminance. SI unit of illuminance is lux. So equipment, whatever is used here is mostly a lux meter. So that lux meter which is used to measure the luminous intensity. How that can be done? Because luminous intensity is absolutely a different parameter. So the unit is candela. So there is a difference between the lux and the luminous intensity. The luminous intensity unit is candela, and illuminance and luminous intensity, they have a very interesting relationship. This is called inverse square law. So the relationship can be stated like it is nothing but the relation between a distance squared. So your intensity E is represented like I, that means the measured luminous intensity, divided by the distance squared. So that means in a particular direction, your luminous intensity is not going to change, but your luminance will change if you vary the distance. So that's why I will be coming to that point again once we will be going to talk about the measurement procedure. But this will be the very important part of our experiment. So the entire objective part of the experiments are classified in a two-way. Number one, to calibrate the text lux meter with a working standard lux meter. Number two, mistakenly, I think both have shown one. Number two is to measure the horizontal luminous intensity distribution of a lamp with a calibrated lux meter. This one, that is basically to measure the horizontal luminous intensity distribution of the lamp, is the prime objective of this experiment. But another, the run one, calibrate of the lux meter, this is an inherent part of all measurements. So we, the electrical engineers, once we do not only electrical, the engineers, we are doing any sort of measurement using a measuring instrument. The first step definitely will come that every time we need to check the calibration. No matter whether we are measuring the voltage, we are measuring the current, frequency, power, whatever parameters we are measuring, the measuring instruments every time is required to be calibrated before we are going to start any measurement. So that is a general standard practice we should follow. Sometimes we don't go that, we directly start doing our measurement using the instrument, but that will not help us. Basically, one, otherwise we will never be able to say whether my measured data are erroneous or not. So that is why my run one, the calibration is not a very separate part of our measurement. For all measuring steps, whatever we are following, that is an already integrated part. But the second run, that is a measurement of the horizontal luminous intensity distribution, is the prime concern, what we are supposed to measure. So as the first part is there, run one, I will be discussing about the run one. This is very interesting. But that entire experiment will be performed on a photometric bench. So why photometric bench? What is photometric bench? You might be thinking of maybe the possibilities are there in your class 2 level physics laboratory. If you have performed some sort of experiments with optics, you might have seen this kind of bench photometer or photometric bench. So it is nothing but a rail which is already pre-scaled. So there is a rail, a fixed rail which is fixed with the pedestal, and over the rail all the elements can move, and you can move it horizontally, you can move it vertically. It's in all the axes that all the individual A, P, L all can move. Okay, so that's why, but at the same time, once you have fixed at a particular point, you can fix it down by steering the screw. So there the attachment is there. So this setup is called photometric bench. This is very popular because the entire rail over the individual components are mounted, that rails already have a predefined scale. So if we want to measure the distance between that two element A and P, we don't need to have a separate scale or measuring tape to measure the distance. It's already the calibrated scale is there from where we can measure the distance accurately. Be careful while we are measuring that. The parallax error may come, so we should take care of that parallax error. That should not be counted while we are doing our measurement. So basically, while we are doing the photometry related measurements, these photometric bench are very much essential. Why? Because number one, the photometry based measurement needs an exact calculation of the distance. A few minutes back, I have told you that we are going to measure the illuminance using a lux meter, but our objective is to measure the luminous intensity. And I have told you the relationship between the intensity and illuminance is a distance square. So we need to multiply the measured illuminance value or the lux value with the distance between the source and sensor, distance square of source and sensor. That will give us the value of luminous intensity. Think about if there is any difficulty to measure the distance, even in a fractional mode, it will just get squared up. So that's why we have to be very much careful about. So that's why here the distance measurement by considering all the possible sources of parallax error, if any, we need to calculate this very accurately. So that is the one reason why we need to use a photometric bench, number one. Number two, our photometric measurements will be much more accurate if we can maintain a specific alignment between source and sensor. So in this regard, I want to tell you one very significant point, which is called photometric center. So if you are willing, you please note down the point. Even in our coming classes, we will be referring many times the photometric center. So this photometric center is a very, very important term in our measurements. What do you mean by the photometric center? Photometric center means a point which will indicate the entire light source. If we want to visualize light source like a point, so a single point which can represent the entire light source, this point is called photometric center of the light source. There is a general rule of thumb, that's a practice, general practice what we do follow is basically the geometric center of the light emitting portion of the source. Because, you know, there is a big source where light part is there, there's a small part is there where luminaire, other assembly like control gear, ballast are placed, we will see later on. But this point is a very specific point where these sources, like only light emitting portion we need to consider, find out the geometric center of this one, that will indicate the photometric center of the source. Okay, so that is another reason the photometric center. At the same time, once we are using a lux meter, that means a sensor, there is a point which is called the sensitivity point of a sensor, where no matter what type of photometric sensors you are using, it may be starting with a very cheap light dependent resistor, LDR, it may be costly sensors like photodiode, phototransistors, and costliest sensors like charge coupled D, CCD, charge coupled devices, and CMOS. In every cases, there is a point at the sensor surface which gives the highest sensitivity. So that point is called the most sensitive point of the sensor. So our all light related measurement, the photometric measurement will be most accurate if the photometric center of the light source is properly aligned with the sensor's sensitive point. If they are aligning with each other, so then we can achieve the highest measured value or most efficient value. So that is why during that measurement, we need to do all possible care. So our photometric bench are required because of the two reasons. Number one, most accurate distance measurement. Number two, here my photometric sensor alignment will not going to get out. Alignment going to get out. So here in the horizontal space, in the left, right, it may get changed anytime. So that's why the alignment should not get changed. It should always be fixed. So that is why the measurement will be most accurate once we are dealing with those situations. Number one is accurate distance measurement. Number two is to ensure the best alignment such a way my measurement will be absolutely free. So that is the two fundamental reasons why the photometric bench are preferred, and our experiment is doing also on that photometric bench. But definitely it doesn't mean always this experiment can be performed with the photometric bench. So this can be performed with any other setup, but using photometric bench, we are going to get the most accurate result. Next, the photometric measurements, once we are talking about, that is a light related measurements, that needs a dark room. So this is a picture from our photometric lab where I was expecting you all to take, but unfortunately, I hope in the coming situations when pandemic will be over, we will be able to meet in this photometric lab. You will see this is the biggest dark room we have. Why dark room? Can anybody tell me? Anyone? Try why we need to have a dark room for this set of measurements? What is the necessity? Am I audible at all?
Yes, sir.
Sometimes you need
So
to just... tell me.
So that we don't have any kind of stray light from reflected places.
Yeah, that's good. But if the stray lights are there, then where will be the problem?
It will get reflected.
No, it's okay. It's reflecting and it's coming to my sensor. Then where is the problem? If it comes there and my measurement is taking care of the reflected component too, then where will be the problem? The problem is that while I'm going to characterize my light source, maybe my luminaire, this light with the reflector or the fixtures assembly, so I'm going to use in any situation. So I don't know what the situation I'm going to take. So my dark room should only measure the direct components, because the indirect component will vary with the different situation. Maybe I have a room where all the walls are painted with white and my ceiling is painted with white. So that means a huge reflections and inter-reflection will occur. At the same time, I can use the same thing in a case where I have almost a dark room. So no contribution of reflected components are coming there. So that's why that all depends upon the designers and the user. I really don't know how to use this. So keeping that in mind, being a designer, being a scientist who is measuring the data, we will always provide data which is for the direct lights. Now your surface reflection, the parametric dimension of the room, that will vary. So that's why the designer who is going to do a design, he will be taking care of those issues. So that's why this is a standard and very important practice while we are performing any photometric measurements, that should be done only on the basis of the direct lights, because the reflected light will be calculated separately based upon the different situation. And once we are talking about the reflection, there is another issue. At what order of reflection we should take care of. So there is an infinite GP series which can be indicated to model this different layer of inter-reflections. This is called retro-reflections. So that's why to get rid of the retro-reflection and inter-reflection, and mostly to take care of the direct lights, we will never allow any stray or reflected light. As you said rightly, we need a dark room. Okay. So, and it's not only simple dark room, the surfaces should also be matte finish. Sometimes your room is painted with a dark black, but this is a glossy, it's an oil-based paint. So lots of lights are reflecting there. So it cannot be considered. So it should be a matte finished. Okay, so that is why it is very clear in our dark room, we have a bench photometer, like a photometric bench, over which we are going to put our source somewhere, and just forget about the P portion. P is another one. So A just source, and L we will put the sensor. We are going to measure the illuminance. So that is the idea. So where the distance between A and L will accurately be measured from the photometric bench. Okay. Any doubts so far? Anyone? Now, okay, thank you. So let us go to the next step, measurement of luminous intensity. So that is our prime concern. But before we are going to think about the measurement of intensity, we need to go for run one, where we need to calibrate my lux meter. So what do you mean by the term calibration? Can anybody tell me? Calibration is very much used in any measuring instrument. In your second year, you have performed the calibration of ammeter, voltmeter, and the wattmeter. You have calibrated, right? In our electrical lab.
Calibration is basically knowing the measurement with respect to a standard value.
Right. So it is represented at percentage sort of error. So the outcome of the calibration should be a percentage error, but it's not an unique value of percentage error, because at each range of reading where you are measuring range of the equipment, your percentage error may vary. So that's why while I'm calibrating an instrument, forget about whether it's a lux meter or ammeter or wattmeter, we should have a standard one. So we have a primary standard, secondary standards, working standard, and we have a test one. So mostly in our laboratory, we are comparing our working standard with the primary standard, or that's how we are deriving our working standard one. And with respect to working standard, we will be calibrating our test instruments. So that is the simple way. Finally, the output of the calibration is a calibration curve. For your better understanding, as I was planning with, so I have made a sort of this thing I will share with you. Last year's one of your seniors instruction sheet I have taken. So this is a calibration curve. Unfortunately, we can't do this. That was plotted where in my x-axis, the lux meter reading was taken, and y-axis the error, percentage error with respect to the standard that was plotted. And that's how we are going to get a calibration curve within the range from 0 to 100 of lux meter reading. So that is very important where, because this value varies continuously. So that's why a unique error calibration value like plus minus 10% or plus minus 5 will not make sense. We need to specify the entire range. Otherwise, it will not make sense. Now, once we are going to talk about, let us come to our case. So while we are going to do our design, so our calibration will be dealing with the lux meter. So to calibrate that, previously what we have seen, to calibrate that we need set of data. For wattmeter calibration, what you have done, you have changed the loads. We have changed the load.
Yes, sir.
So that means to plot a data, to plot a calibration curve, we need to get a wide range of data. Otherwise, we can't plot it. Only a single value will be there, isn't it? So that's why to plot that, we need a set of data. Just like in an ammeter, voltmeter cases, we have varied the load. Wattmeter, we have also varied the load. So for the different range, we calibrated our wattmeter. Here also, to calibrate my lux meter, we need to vary the illuminance range. So how that can be done? So this is the actual concern. How that can be done? How the calibration data? So that's why let's think about, forget about the middle P block. The component A is my light source, which is fixed at the position. L is another point where I will be first putting my test lux meter. Okay. We will be going to take the data. Then I will replace my test with a standard. Maybe you can do the experiment standard with first, then the test, whatever you want to follow the sequence. So let us start test and standard. Compare the percentage error. That will give you the calibrated data of your test one, isn't it? Now, where is the problem in that measurement? Anyone? Are you getting my point at all? Are you getting my point? I said that I will be putting my source somewhere fixed at a point. At a particular distance, I'll be fixing my test lux meter. In the same position, I will put my standard lux meter. I will compare the data, and that's how I'm going to get the percentage error. My question is that where is the problem? So that can be done easily, but will it help me to develop the calibration curve? Will it?
Why not, sir?
Why? Why? I am asking you why it happens. Because once you have put your source on, you have fixed your position, you are going to get a single data. So out of the single data, how can you plot a calibration curve? Because calibration curve will be dealing with the entire range of the measurement for which you are going to use your measuring instrument. So here in this case, how you have the data? Once you have switched on your source, maybe a programmable power supply, and you have made your lux meter test and standard in the same position. So how that values are giving you a set of data. You have a single data. So from the single data, you can plot a curve, right?
No, sir, we cannot plot.
So we need to generate the set of data. Just the way for watt meters we have changed the load to generate the set of data. Here also for this measurement we need to generate a set of data such a way we can comfortably calibrate my test lux meter with respect to the standard and can generate a percentage error calibration curve. How
Then
that can
we'll have to change the position again and again.
Right. So that's one option. So that's why I have given the three options by which we can generate the set of data. The number one option, if we start varying the voltage, input voltage to the source. So what will happen? So if we start varying the input voltage of the source, so definitely the light output will vary. So if the light output varies, we are going to get the different set of data. Number two is a distance variation. So if we start varying the distance between source and sensor, if we are varying the distance between source and sensor, then what you said, there will be also a set of data. And the third one is using neutral density filter. So what is ND filter? I am coming later on. That's so far. Can you say anything on that voltage variation and distance variation? Is it clear? Do you have any more doubts on that?
Yes, sir, not in the first two options, but what is the third option? Neutral density.
Yeah, that I'm coming. Let me tell you the merits and demerits of the first and second. Then we are going to deal with the third one. We will introduce the third one, though in our laboratory we will be doing the first one during our measurements. Here, if we start doing, forget about the P block, again A and L, that two components are there. A is my source who is fixed. Number one, if we can go for distance variation. So if I varying the position of L over the photometric bench, we can get a set of data. Absolutely right. But the variation is not that big. Why? Because I can take L, that means the test as well as standard lux meter, very close to the source, because already I have told you our photometric measurements will be most accurate if we can go by a point source realization. That means my source should be treated like a point who will represent the entire source. So if we can take this lux meter very close to this source, the point source realization will be completely invalid. So my sensor will not treat my source like a point source. So that's how what will happen in a different portion of the source, different contributions will come. So my point source realizations will immediately the point source realization will be immediately fail. So that is what we should take care of. So no matter what type of experiments we are doing, in every cases photometric measurements, we should ensure the point source realization. In the next step, we will be explaining that more interestingly, that how the point source realization is becoming very important parameter for the measurement of intensity. If it is getting violated, we can't do measurement. So the only option, how extended source, this is a bulb. How my sensor will treat a bulb like a point if we can maintain a sufficient distance between the source and sensor, isn't it? So I can definitely vary the position of the sensor, that means the lux meter, both test and standard, over the photometric bench, but I can take it very close to the light source. If it happens, then it will fail the point source realization. So that's why my measurement will be erroneous. So that's why there is a limitation. And you know, the length of photometric bench, what we generally use, that's not that big. Maybe it's something like 5 meters maximum, 4 to 5 meters. So within 4 to 5 meters, if you want to generate a wide range of data, such a way you can plot it, you can't vary that much. So that's why this is really a very good option. But the possibilities are there. You can't get a wide range of data for which you can plot the calibration curve successfully. Number one. Number two, there is another issue. While moving this sensor, test as well as standard, over the photometric bench, my alignment gets little bit deviated. I have told you, though it is a special care can be taken to get rid of this problem, but the chances will be there. While I have taken the data here, next data I can take it here. So in this movement, the possibilities are there. Maybe my alignment has got changed. But this is not a big issue. That should be taken care of while we are doing the measurement at real case. Okay, so that is the distance variation, and that is the limitation of distance variation. Now, what option another we have? Let us fix the test and standard at a point and vary the input voltage of the source. As in our experiment, we are using incandescent bulb. So here voltage variation is a very good approach. Because you know, there are the different lamp families like high intensity discharge lamp family, the LED, that means a solid state lamp family. For them, voltage variation is not a good way to get the output. Even LED, today's LEDs, if we vary the input voltage, then also you will not see any appreciable changes in your output. That is what we need to some extent establish while we are designing the LED circuit, LED driver circuit. That we need to ensure that if you have a slight change voltage in the input side, that should not affect the output. And if you need to change or vary the output of the LEDs, we need to take the help of pulse width modulation or other frequency dimming, different type of technologies. But here for the incandescent bulb, this is a bit easy because incandescent, I don't know why Victor today, right now at 12:52, you are joining. I don't know, Victor, why 12:52 you are joining. You are not present in a class, I have seen. Anyway, so that's how for this photometric page, what we have. Once we are going to vary the input voltage, the possibilities are very much because of the variation of this voltage. So my output definitely will vary with a range that is for incandescent bulb. There is a very smooth curve between the input voltage and the output for the incandescent bulbs. So far in our experiment, we are using incandescent bulb. We are varying the voltage. So voltage variation is a good way because we can vary the voltage from, say, 60 volt to 240 volt. There will be a gradual change in the voltage, so that will not affect that much. Okay. So gradual change in the voltage. But there is another issue. If we vary the voltage, we already have talked about SPD last few classes. Can you recall SPD? SPD? I don't know why everybody is so silent. Are you at all enjoying, or you are somewhere else now? So SPD we already have talked about, spectral power distribution. We already have seen the SPD last day.
Yes, sir.
So here the SPD term, now I think we all are accustomed with the term SPD. Think about the SPD has a very interesting relationship with the input voltage. So if we start adding the input voltage, the SPD of the source also starts changing, and that change is not linear. So that is the disadvantage with this voltage variation technique. So if we vary the voltage, my SPD will vary, and if there is a variation with the SPD, the very much chances are there my sensor, raw sensing element, it may be photodiode, it may be photomultiplier tube, it may be phototransistor, it may be charge coupled device, it may be CMOS. So I don't know how much that raw sensor is sensitive with the SPD, because SPD means there is a shift in the color, isn't it? So that's why if you have a variation of the SPD, that means there will be a variation in the color. If the variation of color is there, so this change will definitely make the sense. So that is why the voltage, even both the sensor, the working and the test, whatever you are using, those are not identical in nature. So that's why I don't know whether the sensor is very much sensible, sensor is very much effective with the frequency or not. That should not be taken care of. So that's why the voltage variation is a method which is very much adapted to generate the big set of data, but that is not absolutely error-free, because with the variation of the voltage, there will be a change, non-linear change in SPD, and as a result, there will be a change in color. So that's why my sensor, whether that is at all affected with the wavelength or not, that we really don't know. Is it clear?
But the error should be very less, sir.
Sorry, what is your question?
But the error should be very less.
No, we can't, because we don't know whether I am using a sensor, raw sensing element, the test and standard, whatever we have. I don't know whether they are absolutely identical or not. If they are different, they may have a very much sensitive towards a particular wavelength, and not that much sensitive with the another. Just a hypothetical source which have two spectra, okay, in their SPD. One is at 600 nanometer, another is at 400 nanometer. Just a hypothetical case. So if we vary the voltage in this case, the maybe at 230 volts, 600 nanometer and 400 nanometer both have some values of SPD. Now, once I am changing the voltage to 150, the variation of 600 and 400 will vary non-linear way. So the sensors who are very much sensitive with the wavelengths, different wavelength of frequency, how they will react with the variation of the frequency and voltage, that I don't know. So that's why if your SPD is changing, so whether frequency or wavelength, that is becoming a function in our measurement or not. Are you getting my point? So if your SPD is non-linearly changing, as a result, whatever measurements I am doing, I really don't know whether my measurement is now becoming a variable with the frequency or wavelength. So that is a part is very important, especially once we are going to calibrate a very sensitive lux meter. But distance variation, that limitation is there. If we vary the voltage from, say, 70 volt to 230 volt, maybe in a range of 5 volt or 10 volt, you can get a big set of data. So that's why voltage variation is a good method to get the set of data, but the chances of error will be there. Okay, so then what will be the third option? The neutral density filter. So ND filter it is abbreviated with. The ND filter, the name suggests that this kind of filter will reduce down. This is basically a kind of optical filter. We can think it's basically a glass sort of optical filter, glass or acrylic type of filter, which is placed between the source and the sensor. So think about the P, where ND filter is attached. So ND filter neutral term is used to indicate that it will not affect your SPD as a nature, only the magnitude of the SPD will be reduced down. So that's why there are the different range of ND filters, 90%, 80%, 70%. So in this way, there are the different ND filters. They will be reducing down the voltage SPDs with a gradual reduced rate. So there will be a factor like 90%, 80%, 70%, 60%, 50%. So that's how, if whatever may be your input, the output value or magnitude of the SPD will reduce, but the profile or characteristics will not change. So color will not get distorted. Only the magnitude of illuminance will reduce. So there would be an attenuation factor, maybe the 80%, 90%. In this way, we represent it for ND filter like optical density, OD. Okay, so ND filter is placed between the source and the sensor. In between, there are the different percentages. The function of that, it will only reduce the value of illuminance without affecting the frequency or SPD. So that is what we need to ensure. So here, ND filters are popular. So what is the disadvantage? Is it clear, the ND filter, functionality of the ND filter?
Yes, sir.
So can anybody tell me what is the disadvantages of ND filter? Let me tell you, this is the best practice because here you don't have any possibilities of distance variation. So that's why you don't have any issues with the alignment, change in alignment. Neither you have any issues with the variation of spectrum which is occurring with the voltage variation. So that's why ND filters can be treated like one of the best methods. But where is the disadvantage of ND filter? Where is the disadvantage? The disadvantage is that it can only reduce down the values. You can't go beyond that ND filter. So the maximum possible value what you can get, that is without the ND filter. So without the ND filter, that will be the 100%. So always ND filter will reduce down the illuminance. It can't increase. So that's why you can get a value within a small range. So if you want to increase the value for voltage variation cases, you can increase and decrease the value. But here, using the ND filter, you can reduce down the values only. So that is the only disadvantages. Is it clear?
Yes, sir. Yes, sir.
Just the way, kind of analogy in this case, it's very interesting. I think you can recall the speed control of DC motors. You have gone through the different DC motor speed control methods. What are the methods? Fundamental 3 type of methods we have seen. The voltage variation,
field variation,
and armature variation, armature control, field control, and voltage. So in this case, for armature and field control, we have one common restriction that is called base speed restriction, if you can recall. So what was that? You can only play with the external resistance which is placed in series with the armature circuit or field circuit. But actual armature circuit resistance and actual field circuit resistance you can't control. Only the thing is that the external series resistance you can make it 0 or maximum. So that's why the field current you are controlling or armature current you are controlling. But actual armature resistance, actual field resistance, that is not in your control. So that will decide the maximum or minimum possible value of current, isn't it? But if you vary the voltage, input voltage variation in any way, so what Leonard or maybe today by using thyristors, so whatever methods we are following, if we vary the voltage, so definitely we can control the speed above and below in both the positive and negative directions, right? So here also I find the similarities over here. ND filter is the best method from the technical point of view. It's absolutely foolproof. But the only disadvantage is that here the only value can get reduced. The maximum possible value is without the ND filter. So that is a 3 method. So but this is one disadvantage, and another disadvantage. I should not say it's a disadvantage because
positive side, sir.
Yeah, the disadvantage here with the ND filter is another. It's really a very delicate thing to handle with, because if your thumb impressions are coming over the ND filters, so that will absolutely change its property. Because finally, it should not be a function of frequency, but your thumb impression while handling the ND filter, that may change the property of the ND filter. So that's why while handling the ND filter, you need to take a special care. Otherwise, definitely it can be a problem. But I am not telling that's why you will not use. It's globally used to go for any standard lux meter calibration. So keeping all this, we have the ND filter as well, but our experiments, we again for that issue we don't use. We prefer the voltage variation. Though there is an error, already I've told you. So is it clear now the three methods and their merits and demerits?
Yes, sir.
So run one is very simple in this case. So I'm repeating the run one. We are only the verge of finishing our run one. So run one, I will be varying. I will first fix up my source. My sensor is fixed at a point. My input voltage of the source is varying from 0 to 240 doesn't make sense, because from 0 to 60 there is no appreciable change. But 60 to 70 to 240, there will be a gradual change which we will vary, and that's how we are going to get the different variation of the data. So that is very much essential while we are dealing with this range. Okay, so that is the one case for the voltage variation. We are varying the input voltage. For your better understanding, I am again referring your senior's data. So if you want, I can share that in the run one. So he was varying the supply voltage from 235.1. Actually, we have taken the test meter as 100 just for sake of our easier calculation. So test meter reading, which was plotted in x-axis in a calibration curve, it was taken from 190 this range. So that's how we have varied the voltage. You can do the reverse also. You can start your voltage from 230, then with the 230, 225, 220, 215. So in this way, you can gradually decrease. But here for better plotting, just to help my plotting part in x-axis, this test lux meter reading will be plotted. So that's why we have taken this 190, 80, and to achieve the 100 using test lux meter, we have varied the voltage from a programmable power supply, variable programmable power supply. So we have got the voltage 235.1. So that's how our ET test lux meter reading was 100 and standard lux meter reading was 106.8. So we have got the ET minus CS, that is the error in with respect to the standard. In the same way, we are varying the voltage 228.1, 220.7, 212. So that's how we were varying the voltage. We have got that. And finally, we have got the value of error, which actually plotted. We can represent it as a bar. So that's what we have seen. The test lux meter reading are plotted in a millimeter graph paper, 10, 20, 30, 40, 50, 60 in this way. And this axis, actually mostly my test lux meter reading were much less with respect to the standard one. So that's why this value was coming in the negative scale. In every case, you can see that the values are in a negative. My standard lux meter readings are more than the test. Test was giving the less value. So that's how ET minus ES. If we take ES minus ET, then it will be positive. So that's how we have got the calibration curve. So now, if the calibration curve is there, so I have got the value of test lux meter 55. So I can calculate if this is my 55. If this is my 55, I can make a projection over here. What will be the error? That will be 3.5 minus 3.5. This will be the range of 55 range. So 55, from there we can calculate the exact value of the test meter reading. That means a corrected test meter reading. Okay. So any doubt so far?
No, sir.
So that means this calibration curve will help me to go to the next set of reading, where we'll be going to do with the measurement of luminous intensity. So measurement of luminous intensity, while we are going to talk about the measurement of luminous intensity, already I have told you This is basically, we are talking about a point in a three-dimensional space. Okay, luminous intensity definition already I've told you, the solid angular flux in a given direction. So we are talking about a point in a three-dimensional plane, and at that point, how much luminous flux is there, that we are measuring. So that is why the luminous intensity, once we are talking about, the first thing will come, the luminous intensity measurement. What is the point in the three-dimensional plane? So if somebody tell you that luminous intensity of this light source is 300 candela, what do you mean? Anyone try?
That the magnitude of the vector is 300.
It doesn't make any sense actually, because until and unless I specify the point where I have measured the 300 candela per candela, it will not make any sense. So once I am going to talk about the luminous intensity, I need to specify a point in a three-dimensional plane. So once we are dealing with a point in a three-dimensional plane, there are the different methods. We know we can have x, y, z linear coordinate system. We can have spherical polar coordinate systems also. So that's why while we are talking about the luminous intensity, the spherical polar coordinate system is a very important part to indicate the point matrix, the entire point in a three-dimensional plane. How? Say, try here, you'll be able to see what actually looks like, but let me explain that. The idea of spherical polar coordinate system represented with r theta phi means, if we have a source, light source, centering the light source, if we have an imaginary sphere of radius r, then we can indicate the any point over the circumference of the sphere by mentioning two angles, one is theta, another is phi. That is the simple idea of spherical polar coordinate system. Centering the source, if we have an imaginary sphere of radius r, then we can represent any point over the circumference of the sphere by mentioning two angles. One is theta, that is a horizontal angle, and another is phi, which is a vertical angle. The issue is that what should be my r? And just a few minutes back, I was telling you the point source realization. Think about, if your source is an extended source instead of point source, what is going to happen? Are you at all?
Yes, sir. If there is not a point source, then sir,
Right.
how will we be able to define
Right.
the immediate one?
Right. So we will not be able to maintain the r uniformly everywhere. So the theta phi concept will not be there. So that's why my r, the value of r is important in that case. The r should be sufficiently long enough, such a way, or the distance should be higher enough, such a way that source, extended real life source, will be treated like a point source to the sensor. So that is the magnitude of r is not important while we are mentioning the theta and phi, because at a particular r, if you vary the r, your intensity will vary. Inverse square law says that. But your illuminance will vary. Intensity will not vary. It will be multiplied with distance squared. So that's why the intensity on a particular direction is not going to change. But that's why if we are varying your r, your actual value of intensity will not going to vary. Rather, your possibilities are there. If your r is sufficiently less, then your point source realization will be completely invalid and you can't use this spherical polar coordinate system anymore. So that's how, if we need to represent a point in a three-dimensional plane, now we can comfortably represent by using the two coordinates only, that is by using two angles theta and phi. So that's why if somebody asks you to provide a luminous intensity distribution data from a source, it should be a 2D matrix, theta angle, phi angle, and the measured intensity. Clear? So theta is my horizontal angle, phi is my vertical angle, that is the intensity. So that is how in a three-dimensional plane we can plot a spherical polar system using the polar coordinate. So in our case, whatever measured data we are doing, so run 2 is much simpler. You already have calibrated, so run 2, I'll be fixing up my test lamp for which we are supposed to measure the luminous intensity. I'll be fixing it up here, and at a particular distance, maintaining the point source realization, I'll be fixing my test lux meter with a proper calibration, because run 1 will give me the calibrated data. I will make all possible corrections. Now, what I need to do, I need to change already to measure the intensity value. What I need to do?
Change the voltage here.
No, voltage, why? Intensity for that voltage will not vary. Voltage is fixed now in run 2 because we are supposed to measure the intensity at that particular voltage, intensity data. Different angles we need to vary. Already I have told you at different point the intensity will vary in a horizontal angle and vertical angle. So that's why I have told you the intensity value somebody specifying you at 30 candela doesn't make sense, because we need to specify at which angle of theta and which angle of phi. So that's why the 2D matrix I was talking about, if we forget about the vertical plane, in a horizontal plane, if I want to plot the intensity value, what it is going to give us? What?
Polar coordinates, just one theta or just one angle.
One theta, right. So that means I need to then rotate, centering that source, with a radius of r, I need to rotate the sensor at a different angle, such a way for the entire 360-degree circle, I'll be able to get the set of intensity data, isn't it?
Yes, sir.
So first I will be fixing at 0 degree. Then I can make it 10 degree, 20 degree, 30 degree. So that's how centering the source, maintaining a sufficient distance of r. If I rotate my sensor at the different angle, then only I am going to get the data, all the 360 degree data in a horizontal plane. Because here we are not changing the vertical point. So my phi angle is now fixed. Phi is 0 here. Only the theta is varying. Do you agree with me or not?
Yes, sir.
The last thing is that in this case, this will be a little bit cumbersome, because within the laboratory premises, especially if we don't have sufficient place. So here, if we are start changing this with a bigger radius, it will be quite impossible, because I don't have that much of place. So what else I can do? I can't compromise my distance. If we compromise with the distance, the point source relation will be invalid. So what next to do?
We can reduce the size of the source.
No, that's I don't have, because somebody has given you a source, an incandescent, and ask you to measure. You can't ask him that please reduce down the source size, then only I'll be able to measure. That cannot be done. I have given you a source, now you have to use your brain and do the measurement.
So then for the places where we have more space, only that angles we will measure.
No, I am asking you that give me the 360 degree angle in a horizontal plane. What can you do? Is it possible at all or not without moving this one? I can do it. Why not? Because I can fix up my sensor and allow the source to be rotated along with its own axis. Are you getting my point? So it's a relative displacement. So instead of fixing up the source and allow the sensor to be rotated with the 360 degree, I'll be fixing up the sensor and allow the source to be rotated at 0 degree, 5 degree, 10 degree along with its own axis. Then also I'm going to get. Do you agree with me or not?
Yes, sir.
So let us fix up my sensor, and source is rotated. The linear position of the source is not changed. That is fixed. But the source will be rotated over with its own axis from 0, 5, 10 in this axis, and I'll be noting down the data. So then also the relative displacement will be there. So I need not to rotate. My R is maintained sufficiently high, such a way point source realization is not invalid. but at the same time, I am getting the different angles to get the data. Any doubt with this? Just feel free to ask, because this concept.
So this is better method. In fact, less error will be there if you rotate the source.
Yeah, absolutely, because that is a better method. So that's how we are going to get the set of data. So I'm again sharing your senior's data. So what he measured by following that method. So just see uh, 0, 10, 20, 30. So different angle. Can you see that? Is it visible?
Yes, sir.
So the distance maintained was 1 meter because the source size was not sufficiently big. With this 1 meter distance, the source was rotated along with its own axis with 0, 10, 20, 30, 40, 50 in this way. And that's how all the standard test meters readings were noted. Illuminance meter or lux meter reading was noted. Then from the previous calibration chart, corresponding calibration errors are calculated. And that's how the exact corrected value of the lux meters were given. We have multiplied that with distance square to get the intensity. So that's how for different 0, 10, 20, 30, 50 in the different angle, we have got the entire intensity values. So that's how for the, just see, for 360-degree angle, we have got the intensity values. Okay. So that's how we are. Now the last thing is that we need to plot that in a polar graph paper. So the polar graph paper is very simple here also. Here you can see this is a standard graph paper. What you have, some angular sectors are there in the graph paper and some concentric circles. If you see the graph very carefully, first phase is to prepare your graph paper. To prepare your graph paper, the first thing is we need to find out how many concentric circles are there. Are you getting my point? So there are the different angles, angular sectors and concentric circle. Let's remit 0, 10, 20, 30. In 10-degree interval, we have all the points. Now, this step is very interesting. First, find out what is the maximum value of your measured intensity. I am referring your senior's data.
Oh, so the maximum value then will become the largest concentric circle.
Absolutely, absolutely right.
Then the rest will be scaled accordingly.
Right. So the outermost circle, whatever we have, so this will be assigned with the maximum value of intensity you have got, and the innermost circle you have assigned the minimum value you have got. Or else, if you have a fractional value, say your maximum value is coming, say 81.6, and minimum value is coming 29.4. You can make it a round off to get the uniform value of all circles, because all the concentric circles are the uniform gap. So that's why you can make it say 90, 80, 70. So in this way, all the uniform values are given. So the maximum value or more than maximum value at the outermost circle, and innermost circle minimum value or something less than that. So that's how the entire part is plotted. The maximum value and the minimum value, that's how they are basically plotted. Are you getting my point? So that means in my outermost circle, I'll be assigning the maximum value or some round of value or some very round of value near more than the maximum value. 86.1 is my maximum value. I can assign the outermost circle like 86 points. So the entire outermost circle will 86.1 candela. And the innermost circle is 26.5. So let us give the innermost circle as 26.5. So now at each value, we need to find out the same uniform intervals. So same intervals. So that's how we need to find out the same intervals accordingly. But it is very difficult, isn't it? So the 86.1 and 26.5, count how many circles are there, divide that, and that's how very fractional values will be assigned to the individual circle. So you can do a better way. So that's all about you, how you can deal with the situation. you can assign the outermost circle with a 90 candela and the innermost circle of almost this point as 20 candela. Now find out how many circles are there. Accordingly, with the uniform value, you assign the values to the individual circles. So that is step 1 is over. I have already assigned the value. Next plot is plotting. So next step is just to plot. Sorry. To plot that, again I am referring Pritham's data. Say, just in this case, at 0 degree, I have got 66.9. Or just as this is not equally plotted in the graph. So here at 0 degree, if I see this is my 90 degree circle, this is my 80 degree, this is 70 degree, this is 60 degree. 66.9 will be somewhere here. Plot that point. Now at the 10 degree, find out the value what you have. 65.7. At 10 degree, this one is 10 degree. 10 degree, again 65.7 is there. So in this way, at each degree of your measured data, you plot the point individually by taking care of the candela circles, individual circle which represents the candela at that particular point. And that's how finally a curve will be plotted. Like finally they will be joined. I can't say the best fit curve, because if you want to draw the best fit curve, the chances will be there. Some of the points are omitted. I'll be asking that something which is very smoother. So that is a kind of curve, whatever plotted by them. So here I have provided him that curve. So 0 degree, 10 degree, 20 degree. So that's how, just see the 80, 70, 60, 50, 40, 30, 20, 10. So that's how he have divided the candela circles, right? So the outermost one is the 80 candela, then the 70 candela, then the 60 candela. So that's how regular interval the candela values are there. So at 0 degree, he has got something he plotted. At 10 degree, whatever value he plotted. 20 degrees, so all the values are plotted, and finally they are connected with a smooth curve to form the polar graph. So that is how luminous intensity curve, what actually we have got for this case. And there is some sample calculations so that I can share that to calculate this calibration data, how we can interpolate. Sometimes it's my calibration curve is not linear in nature. We need to interpolate the values if we have. So how the interpolation can be done, so that is shown over here. So with this, the polar graph. So any doubt so far about the plotting of intensity of polar graph?
No, sir. Plotting is simple, sir.
Very simple. The last thing, a little bit, some advanced equipment, maybe in your next year, once you will come to Illumination Lab, because already I've told you, we need to deal with the basically a theta as well as phi. That means we need to deal with a sphere rather than a circle. So in our measurement, we have plotted a circle because the vertical part we haven't considered. The only horizontal angle we have varied. But in reality, once we are dealing with the biggest source, we need to measure the horizontal as well as vertical. So that's how the intensity data, whatever are plotted, that is as a 2D matrix, theta and phi. So that's why there are some equipments we have in our laboratory, like large photometer. So this is used for measurement of luminous intensity for theta as well as phi. We have seen the bench photometer, that is only for the theta for incandescent bulb, but for this is a big source, we need to measure the theta and phi. This is a very old one, and this is another, the distribution, mirror distribution photometer. So I'll explain it later on, because this experiment is there in your 4th year. So you'll be performing that experiment. We will talk about that, why the mirror is there. But this is a big source we are going to measure, and it's a fully automatic part. We have several drives and automatic system. And this is a very new one we bought last year from one big project. So this is a mirror photometer. So that is a fully automatic one, SCADA-based system by which we can measure the intensity value of any size of source. The two of this equipment we bought this. Just I've shared with all of you because I can't take you to the laboratory. Every time I used to take the third year students in the laboratory, I after the experiment I show them that what the actual measuring methods are there. But unfortunately, this year because of the pandemic, we couldn't make it. I hope very soon we will be again meeting. So with this, I conclude our today's session. If you have any query, just feel free to ask me. Any doubts, any query?
No, sir.
So what I can do that if you want, I can share this recorded one to all of you. And also the report what already I have with Pritam. So I will be expecting that we using that data, if you can develop your own report and submit that to me. Unfortunately, we can't do that. One more thing I can add to all of you, what Pritam has already plotted, that plot manually you try to do that. Don't copy from him because already the measuring data we are taking from him actually. Using the data, you try to plot your polar graph with your own manually, as well as using a MATLAB code to plot the polar diagram.
But the data will be same than the
Yeah,
plotting.
absolutely same because there is, I know that there is no such, but I will prefer that unfortunately in this situation, I can't take to our laboratory, all of you, and we can't go by this measurement. At least you can see how the polar graph is plotted, how using MATLAB you can write down a code. So that's using the same data. I know that this is not the entire thing because until unless you are doing your experiment with your own hand, it doesn't make sense. But still, as this situation, we are helpless. We all are helpless. So in this situation, at least using that data, if you want to start something, that will be, if you want, so you can do that. And I prefer that if you submit a small report on that because we need to go by some formalities also. So I am sharing that the entire report to all of you. Individually do it and make it a comprehensive one.
So should we submit the conventional type report? I mean,
No, actually, only the title objective you write down. Rest of the things doesn't require. Only the calculation. Here I am sharing that report. The calibration curve, instrument, different apparatus list like incandescent lamp, 2 lux meter, the programmable power supply, as I said, optical bench, and optical mounts to mount the lux meters, sensors. So that's optical mount. So that is a standard. Use the apparatus list, the title, and the data and the graph. And this portion, the remarks, because you haven't performed the experiment, but from the today's discussion, if you have anything special you have observed during our discussion or some question which has been raised, if you just write down this in a form of remark, that would be great.
Okay, sir.
okay, sir.
Okay, thank you all of you. I hope if you don't have any query, then we can skip. This week again Friday, right?
Yes, sir.
Yes, sir.
Friday.
So Friday that time around 12:30.
Yes, sir.
Okay, see you all in class on 12:30 this
Okay,
Friday.
thank you, sir.
Thank you all.
Thank you, sir.
Thank you.